Okay, so welcome everyone to another great RISC-V technical session. This time we are going to learn a little bit about the hardware-based detection of stack buffer overflow attacks on RISC-V. And today's presentation is going to be, conducted by Cristiano and Alessandro, both from Politecnico di Torino in Italy. Cristiano is a PhD candidate and Alessandro is an associate professor. So Alessandro, please go ahead and start the presentation.
Thank you so much. Well, first of all, also thank you for inviting us, and being here is really a pleasure. I can say that either for me, but also from Cristiano that will speak later. Well, let us start with a bit of publicity, in the sense, a context about the group and where the work that we are going to present was conducted and funded, basically. So we represent today the Smileys Research Group, which is a research group from the Politecnico di Torino, and precisely from the Department of Control and Computer Engineering. We are a multidisciplinary team. Together in the attendees, there is also Professor Stefano Di Carlo, who is the leader of the group. We cover many aspects of the computer continuum, because we work on resilient computers, but also on cybersecurity and artificial intelligence. And kind of surprisingly, we cover also computational biology, but we actually think that the heterogeneity of the members' background is pretty important, and actually that also here in what we're going to talk about in a sense. And another couple of information, because the work we are presenting today is part of a work conducted in two funded projects. One is a European funded project, which is Vitamin 5, led by the University of Barcelona. And this project aims at porting the cloud environment basically on RISC-V, and vice versa, so providing the means for covering that part. And we cover many countries in the European landscape. As you can see, the partners spans from Greece to Portugal, and also Northern Europe. Let's consider them too. And another project that it's part of the deal here is an Italian project, which is SERICS, and within SERICS, the Sandstorm one, in which, from more on hardware perspective, I would say the point is develop an open and secure architecture based on RISC-V. And we are kind of embracing also the European process initiative. So this is inside all of them. And also here, let me spend just 1 second saying that we cover many part of Italy in this case, since it's a national project, because there is the Politecnico di Torino, but also Genova and Pisa and Cagliari, and also some industry partner. Okay, that's it for the publicity. Let me also kind of give you a perspective about the presentation that is going to be composed of two parts here. One would be conducted by me, the first part with context and background, and the second part that will cover more technical information about how you can detect malware using hardware feature. Basically would be conducted by Cristiano. So my role, first of all, is giving you some perspective of why you need to work on detecting cybersecurity threats that are then considered attacks and malware. Because basically, if you read out there from many sources, this issue is not also bigger. It's considered one of the most important issues, and it's also costing a lot of money. And these two factors together are kind of leading not only the research but the investment in the field. And why? Because well, you know already, probably because you are connected here, that the complexity either of the hardware or the software, or basically most of the time both, is growing a lot. And this complexity is giving us a lot of powerful tools, but is also creating a lot of blind spot where attacks like malware can hide and go. Another thing that is important to define today, so that you will understand even better the technical content, is where we want to go. I'm not going to say that we are already there, but our results are kind of confirming that the way is exactly the way that we are paving today, together with other researchers around the world, which is arriving to the capability of providing zero-day detection. What means zero-day detection? It means that the detection capability in your system will not be based on previous knowledge per se, but wherever new malware arise, the deviation on what you're going to observe is going to make the detection possible. And this is going to tell you, okay, there is a malware in my system, even if it's the first day that your hardware, your software are seeing this attack. Clearly, this is a kind of a golden goal. And to arrive there, we still need to work a little bit, but this is where we are going and where we want to go. So another role in this presentation for me is giving you some malware fundamentals that are keywords and concepts that maybe you are already aware of. And if you're not, then it's my role to give you some idea here. Uh, Categorizing the malware is pretty difficult because they are very different in some extent and they're very similar in others. But basically, if you want to categorize them, you can find three common properties. First of all is the kind of propagation methods for them, which is basically their purpose, how they expect to spread around the world. And another important property is the concealment strategy. So if they plan on concealing their presence, their data gathering, everything, or not. In case of stealthy malware, this clearly means also that the detection will be probably more difficult, but we will talk about that later. And another thing that is very important as a property is the kind of manipulation in the data/control structures that leads to the attack to be there so that the malware can exploit. There are different scenarios. What we are going to concentrate today, because we are going to talk about stack buffer overflow as a mean for the attack, is the memory corruption and specifically the control flow attacks. In this case, it's exactly where the stack buffer overflow will place itself, because it's going to change the control flow in many ways, and we're going to talk about that later too. Here, to summarize the many malware type that you can probably know already, you see the three properties displayed in the table, and you can already notice in the concealment strategy especially that since most of the time there is a concealment, and this is based on polymorphisms or encryption, you can expect that just looking at the code, as we're going to say later, it's one of the things that you can do a static analysis. This is going to make your life really difficult to spot the malware as soon as possible. And on another extent, the zero-day detection that we claimed as a final goal, it's even more complex if mutations are one of the bases in the detection, and this is what you're going to use. In terms of the detection itself, so the strategies, the methodologies, and how it is performed nowadays, the majority of the techniques that you can find out there, and probably you are most aware of, are software-based techniques. There are already some hardware techniques, that is the subfield where we're going to show some specific methodologies and results, but most of them are still software-based one. Software-based means basically that the idea is analyzing the software either in a static or in a dynamic way, or both, basically, to extract meaningful features, and this is kind of common in all detection and classifiers. And this is also a mean to say that most of the software techniques, they require big data sets and a huge amount of data. And as we're going to say also later, this can be a problem because it means that in the local edge existence, making the detection possible would be difficult because the final model of the detection would be big. In terms of software, the general approaches can be summarized in four of them. First of all, you can go for signature. So you are basically looking for the malware. And in this case, you try to figure out a signature of the malware. Uh, this is static most of the time, and it complements with the behavior-based approach, which means that you are going to still find a sort of a signature, but more based on the dynamic behavior of the execution. Clearly, you can see already that here, these two approaches, they are not a good fit for the zero-day detection, because basically, if you require a signature, then you need to know that there is a malware so that you can provide a signature. There are other two kind of common approaches. One is based on heuristics, so machine learning in general, and especially when the data that is going to be collected is starting to get bigger and bigger, then a lot of new approaches are going toward deep learning, but probably this is kind of expected nowadays. Based on the hardware approaches, let us start with defining what you are going to observe. What is the meaning of going software? Basically, it's a well-known field, the analysis of microarchitectural features that are exhibiting different behaviors depending on the software that is running. So this basically means that let's say from a signature perspective, you can expect to observe the microarchitectural events in your system. So let's say misses in the caches or the patterns of load and store from memory to be different depending on the software that is running. This is already known because you know that probably in most of the modern hardware microprocessor nowadays, it's already several years, you can find hardware performance counters. What hardware performance counters are? They are basically counters that are connected to specific microarchitectural events to count exactly the amount of these events. The amount in time is basically the shape of what is happening. So the expectation in detecting malware using hardware-based approach is to translate these events from just an observation for performances into an observation that, coupled with machine learning / AI techniques, can provide a sort of detection. Okay. Hardware-based detection is not a new field. It's already there from several years. And basically, in this slide, you can spot some kind of time shape of what happened. In 2011, some work, Malone is one of them, was basically proposing the analysis of hardware events as a mean for detecting code modification. Okay, stating on a paper that if you are observing these events and the code is doing different things, you can basically spot the difference. In 2013, this kind of idea was moving toward a real detection for Android malware and the Linux rootkit. And since this is not only research, probably I don't know where all the attendees are coming from, but I expect that someone from industry is out there. This is already exploited on some extent into the industry, because as you can see in 2018, Intel developed a technology, actually make available a technology, which is the TDT technology, that is targeting specifically at the beginning ransomware attacks, and is resorting, if you look at the manual and the technical explanation, to some sort of CPU telemetry, which is basically another way of saying hardware monitoring of some sort. And this is already coupled with machine learning. So the idea of the threat technology is already to couple the observation into the CPU and some machine learning to help exploiting the data. Eventually, another very important event in the field is in 2021, when Microsoft made available this Defender for Endpoint, which is a sort of an integration with the Intel TDT. And among the other things that the Microsoft Defender Endpoint does, there are these endpoint behavioral sensors, which has another wording, let's say, to say observation of hardware events. Before diving into some more technical details from Cristiano, let me just spend still some couple of minutes to base also some pros and cons in hardware-based detection, because our role here today is not only to explain what we did, but also to ponder if this is a very promising research field or not. And basically, looking at the pros, as we are going also to observe in the results, using hardware detection based approaches makes the feasibility of runtime detection more prone to be available, because as you probably already imagine, when you gather a lot of data and the data has to go on the cloud, then basically this means that the detection cannot happen in real time, but it has somehow to happen in a while. With hardware-based detection, this is feasible. The zero day potential would be showing the results. Also, because looking at the deviation in the hardware performances, then it's more possible to observe a kind of a common scenario, and also that there is the even more important point, to train only on the known data, which would be always the benign application, so the application without the malware. Other things that you can expect are the resilience against some malware that is trying to subvert the protection mechanism. Since you're going to work at the hardware level, you can be more resilient in there, and also a reduction in cost. Together with the pros, let us also say something about the cons. Probably the most disputed one is about the accuracies. Results in the literature are so far displaying accuracies that are not in the very high range. The average is around 80%. Some, as you can see in the table, they report some better accuracy. And the point being here that if you don't have a high accuracy, then you can say, okay, this is not the proper technique for me. But on the other hand, you can also say that even if the final accuracy is not perfect, you can always rely on the actual scenario, on this accuracy as a starting point to select whether something is not affected by a malware, and maybe run some further analysis on more data later on. Also, other things that are open to discussion is on the hardware side, the performance monitoring units that are available right now, they are limited in the number of counters and events that can be activated at the same time. And we're going to discuss that later on, also showing the results, but this can be a huge drawback so far. But probably, since we are into the RISC-V community here, this is an open field to work on. So very quickly about these hardware events, so that everybody is on the same page before starting digging into the technical results. Hardware events are usually available through PMUs, and the working scenario is I know the list of events that my CPU is supporting, so the kind of events that I can track. I can look at them from a performance perspective, as I will say, and now in hardware detection, I can find among them a significant one to track the differences in the behavior that is happening, depending on what I want to detect, in this case, the malware. The other thing that I have to do is to figure out how many counters I can really activate, so how many of them I can track and read all the time. And basically, all the CPUs have a mean to program this kind of connection. Clearly, tracking the performance counter means basically two things. One, which is the mandatory one, is that you are going to observe the deviation in performances through time. So in order to track the differences in the behavior, you can either position yourself in many points in time, so observe them as they evolve, or you can observe them as a cumulative effect at the end. And this is one of the one important thing. And the other thing is that reading the performance counter, they also are prone to attacks because they are a side channel actually. As I see in the comments on my left monitor. So you are right, and this is a thing that clearly at the end would be inside the pros and cons. So this is something that has to be pondered. But first of all, from a detection perspective, what is important is to have as many events available. So the final message at the end will also be that at a certain point, maybe even more events will be needed, but this is to be discussed later on. So this is the end of the first part, and now I left the floor to Cristiano, which is going to dive you into the methodology for deploying hardware-based malware detection really on the field and on RISC-V microprocessor too. So I will stop sharing.
Okay, do you hear me?
Yep, everything is fine.
Okay, thank you, Professor Alessandro, so far. And here we will go deep on the hardware-based malware detection approaches. Here we have the framework of the HMD approaches, and this framework is a guiding structure to facilitate the implementation of these approaches. The hardware monitoring units, they are already available in modern processors. Therefore, the idea of this approach is to leverage this infrastructure already existent in modern processors. The HMD framework consists basically in data collection and pre-processing of this information provided by the hardware, and later on the malware detection process itself that is implemented by machine learning classifiers. At the end, we will be able to classify some software or some application as a benign application or as a malware. To perform the feature extraction, we can use some strategies. Therefore, for training the machine learning models, we can use, for example, microarchitectural simulators like Gen 5, or also GVSOC, that is the simulator provided by the PULP platform that we use it, and we will talk a little bit more on the next slides. The other strategies that they are mainly used during the test part of the approach, or also in the real-time detection. we can use for feature extraction the employment of a library, like for example PULP, or use a proprietary kernel module, or also some utility like perf. The feature extraction, it could occur in the time domain or also in the event domain. About the feature selection, that is the second block in the data processing from the hardware side. The feature selection itself, it brings some advantages that they are addressing the curse of dimensionality in machine learning. They enhance the data understanding, they reduce the computational requirements, and they, of course, also improve the predictor performance. As algorithms to implement the feature selection, filter-based algorithms, they dominate the field of hardware-based malware detection. And some examples of these algorithms, they are the principal component analysis, Fisher score algorithm, Pearson correlation coefficient, and also information gain, that is also called mutual information. As tools to implement these algorithms in the hardware-based field, they basically the studies, they basically use the scikit-learn library for Python and also the Weka framework. About the malware detection itself, as I already told, it is basically implemented by machine learning classifiers, and these algorithms, they can be supervised or unsupervised learning techniques. We have some pool of machine learning algorithms that implement this classifier, and here we have some examples. They are, for example, artificial neural networks, support vector machines, more simple like logistic regression, more complex like assembly learning, decision trees, k-nearest neighbor, rule-based, and also linear regression. All of these are machine learning algorithms that can perform the classification in the hardware-based detection approach. In this table, we have a selection of the main studies and main published researches in the field of hardware-based malware detection. And we can see that among these main studies, there are no RISC-V studies. There are no works that they try this approach, this hardware-based approach over the RISC-V devices. And the idea of with our work is also to cover this space that is not still well explored. Here we will enter in our case study, that is the detection of stack buffer overflow attacks on RISC-V devices. This study is we are still working on this research, but we have some interesting preliminary results to show here. A little about the basics of the stack buffer overflow attacks. they they intend to redirect the program execution flow to a malicious code through a non-validated input data overflowing a buffer overflow, a buffer allocated in the memory stack. In this figure, we can see that before the SBO attack, the stack pointer is pointing to the local variables, and after the SBO attack, we overwrite the return address in the stack. Therefore, overwriting the return address, we can redirect the program execution to a malicious function, and therefore in this way perform some malicious attack and action. After to this malicious code execution, if we overwrite again the return address, we can go back to the normal program execution, and in this way the malware, the malicious code, can stay stealthy, or in other way, in a transparent way for the user. In this case study, we employed a RISC-V implementation that is known as Parallel Ultra Low Power Platform, PULP. It is an open source programmable architecture targeting the computational requirements for Internet of Things applications. The core that we used is the RISC core from the PULP platform, that is also known as CV32E40 core. It is a 32 bits and 4 stages pipeline. Here we have some simple block diagram of this core. The PULP platform made available a simulator that it is called GVSOC simulator, that is a event driving tool with a hardware-oriented description. And this is the simulator that we employed in our experiments. The main contribution of our work in this case study is to analyze the performance of the hardware-based malware detection approaches in detecting stack buffer overflow attacks. But with this work, we also intend to contribute on the discussion of zero-day detection using the hardware-based approach, as the Professor Alessandro told us. We also aim to contribute on the discussion of the security of RISC-V architecture, and also we aim to contribute on the analyzing the performance of the classifiers for anomaly detection. That is a branch of classifiers that we used in our experiments. We include in this investigation the advanced techniques such as autoencoders to improve the detection of these traditional anomaly detection classifiers, and we will show some results that we got from our experiments. A little background on this topic. We employed anomaly detection in our case study. As we can see in this figure, in anomaly detection, the classifiers are trained only with benign applications, that in this figure, they are the white dots. basically in the center. Therefore, the dots that they are far from these training observations, that they are the yellow dots in this figure, they are considered an anomaly. And in our case of security, they are considered some malicious threat. The advantages of using the anomaly detection branch of machine learning are basically two. The first one is that the anomaly detection does not require a malware dataset for training. And the second is that the classifier can perform zero-day detection, what is very important, very interesting, as again the Professor Alessandro told us. A little background about the autoencoder. Autoencoders, they may be used to learn features for classification. Therefore, autoencoders, they may be used before the classification as a tool to increase the accuracy of the machine learning classifiers. An autoencoder is an unsupervised feed-forward neural network that is trained to copy its input to its output. In this figure, therefore, we have the autoencoder that we implemented. It is composed by an encoder and a decoder. And between the two, we have a bottleneck that is a layer of this neural network that has less nodes than the previous layers. Therefore, with this bottleneck, the autoencoder forces a learning of the most important, of the most salient information in the data, and therefore in this way helping to improve the accuracy in the classifiers. About our methodology. Our methodology is composed by a simulation environment and the implementation of the hardware-based detection framework, as we can see in this figure. In our methodology, we propose a technique that we call single analysis per detection. What is this? We performed the collection of the hardware performance counters just at the final of the execution of the application execution. These techniques has a big advantage and a big disadvantage. The big advantage is that collecting data from the hardware just at the end of the execution of the application execution, we have less data to analyze in our machine learning classifier, therefore reducing the computational effort. But this is an advantage. On the other side, this technique imposes a higher challenge in the malware detection. Why? Because analyzing data just at the end of the application, we cannot grab fast deviations on the data. Therefore, in this way, we have a challenge in the malware detection, but on the other side, we have an advantage that is the reduced computational effort in the machine learning side. Our in the simulation environment, we have the target applications, and the target applications, they are composed by vulnerabilities artificially inserted, in our case, by a malicious code, that is where the code is deviated after the stack buffer overflow attack. And we use it as a malicious code, in our case, a Fibonacci number generator. We have also, in the target application, a function to read the hardware performance counters, and mainly we have the benchmarks. We used 4 benchmarks, that they are the AES encryption algorithm, the RSA encryption algorithm, the secure hash algorithm, and the Dreizka algorithm. All these parts, they compose our target applications that receive stimulus from the stimulus and attacks from the control scripts. A little bit more about the malicious code, that in our case is the Fibonacci number generator. As in our case study, the detection of the SBO attack is dependent on the size of the malicious function. We expressed our results as a function of the size of the malicious function, and we defined to use malicious functions with size of 1% and 10% of the size of the benchmark. As a metric to measure the size of the benchmark, we used the number of instructions executed. A little bit more about the control scripts. The control scripts, they basically define 3 execution modes for the simulations. The first execution mode is the benign. That is the situation where there is no attack. In this figure, we can see this execution as the green line. The execution is a pure execution of a normal application. Later, the second execution mode is the overt mode. In this case, the attack takes control of the execution without returning to the caller. In this mode, in this figure, is represented by the orange line, and we can see that when we have some vulnerability that is successfully exploited, we have the execution of the malicious function, and after the end of the execution of the malicious function, the normal execution doesn't happen. In other way, after this malicious execution, the execution of the application is closed. In this execution mode, an eventual user may note some strange behavior on his application. The third execution mode is what we call it the stealth mode, and this execution, in this execution mode, after the attack and the malicious execution, the program execution returns to its malicious, it returns to its normal execution flow until the end of the execution of the application. In this stealthy mode, we have a scenario when we are more close to the most malware behavior, and in this case, the eventual user, it may not see the execution of a malicious code because it is stealthy. About the feature extraction, the feature extraction was performed by us in the GVSOC simulator through its application programming interface that is provided by the simulator. In each execution, the input stimulus of the benchmark is randomly varied. Also, in each target application, we executed 10K executions without attack, and as anomaly detection, we used the data resulted from these executions as a training data set. And besides this, we also performed for each target application 10K executions, mixing between executions without attack and executions with attack. And based on these 10K executions, we assembled the data set for testing our approach. The feature selection is implemented by the scikit-learn library for Python. We employed as algorithm the principal component analysis to build a ranking of the hardware performance counters. And in our case, even that PULP platform doesn't offer a huge number of hardware performance counters, the feature selection it is important because in most of the processors we cannot monitor a lot of hardware events at the same time. Therefore, it's interesting to build a ranking of the hardware events and the hardware performance counters available to enable a selection and prioritizing of the hardware events analyzing when we implement the approach. As classification models, we use it for classification algorithms that they are designed for anomaly detection, and they are the one-class support vector machines, the local outlier factor, the isolation forest, and the elliptic envelope. These classifiers they were also implemented in the scikit-learn library for Python. Now we start to talk a bit about our results. Here we have the results of the hardware performance counters ranked according the principal component analysis. And these results, they are expressed for individually in an individually way for each target application. We can see that in a general way, three performance counters, they stayed in the first position of importance among all our benchmarks, and in the sense that these three hardware events, they are the most significant information for our analysis. These three HPCs, they are the instruction count executions, the load executions, and the RVC, that are the compressed instructions executed. Here we start to see some results about the stealthy mode. That is a mode where the malware, the attack, could happen in a transparent way, let's say. As I told you, the results, they are expressed as a size of the malicious function in comparison with the size of the benchmark, and we have the results expressed as a size of 10%, that is the upper histogram, and results expressed when the size of the malicious function is 1%, that is the lower histogram. Some interesting results. If we analyze application by application, we can see that the AES encryption, the SHA algorithm, and the DRISC algorithm, they have an accuracy higher than 90%, even with a malicious function of 1%. We can see this on the lower histogram, and we can see that with some specific classifiers, that they are mainly the local outlier form classifier and the elliptic envelope, we can have accuracies higher than 90%. On the other hand, the complete RSA encryption, we have an accuracy higher than 90% just with a malicious function of 10%. And we can see this in the green rectangles on the upper histogram. We can see that with a malicious function of size 1%, the accuracy detection in this RSA application is, let's say, very poor. We deeply investigated this, and we noted that this pure detection with this application is due to the randomness on the generation of the public and private keys in this RSA application. Therefore, we made a try fixing the generation of the keys, fixing the keys in order to eliminate this randomness and to see the accuracy behavior with a situation with the keys fixed, with the fixed prime numbers that generate the keys. In this case that we can see in the center of the histograms, the accuracy was higher than 90%, even with a malicious function of size of 1%. As a conclusion, we can see that the randomness in the RSA application is a challenge for our approach. If we ponderate about the performance of the four classifier algorithms used, we can see that the LOF classifier, the local outlier factor, is the classifier that better performs. It is the only classifier that presents accuracy close to or higher than 90%, even when few hardware performance counters are considered. And we can see this in the arrows, in the black arrows pointing in these histograms. If we consider the LOF classifier in the AES, RSA fixed prime numbers, and SHA applications, the last, the bar on the histogram more at the left is the accuracy when we consider just one hardware performance counter in the analysis. And we can see that this blue bar, considering just one hardware performance counter, the LOF classifier presented a good accuracy or higher than 90%, even just one hardware performance counter taking in consideration. Here we have a plot of the principal component analysis for each benchmark. We can see here a visual explanation why the performance was lower in the case of the RSA benchmark. We have a lower detection performance in this case because the red dots that they represent a situation where we have an attack, and the green dots that are normal executions, they are very intricated. They are very close, let's say, imposing a challenge for the malware detection. Here we have some results comparing the situation when we have no employment of the autoencoder before the classification, that is the upper histogram, and the situation where we added the autoencoder before the classification. Comparing this upper and the lower histograms, we can see that overall there is no significant gain with the addition of the autoencoder. But there are two interesting things that the one class support vector machine classifier, it basically only increases its performances when we use the autoencoder. And we can see this in the flag, in the red arrows on the lower histogram. On the other side, the elliptic envelope classifier mostly decreases its performance. And we can see this on the green rectangles in the lower histogram. We can see that without using the autoencoder, the elliptic envelope sometimes offer a good accuracy, and when we add the autoencoder, the accuracy of the elliptic envelope was drastically reduced. Here we have some results for the detection in the overt mode. This overt mode is the mode where after the execution of the malicious function, the execution of the application is closed, is finished. We can see that if we analyze in terms of applications, the AS, the RSA with fixed keys, fixed prime numbers, the SHA and the DRISC, they show an accuracy of at least 94% with the malicious function of 1%. And we can see this in the red rectangles in the lower histogram. That is the histogram of malicious function of 1%. And this accuracy is quite interesting. On the other side, we saw that the complete RSA application with the randomness of the key generations, it has a good accuracy, that it was 99%, just with malicious function of 10%. And this is illustrated with the green rectangle in the upper histogram. Analyzing the performance of the classifiers, we can see that the LOF and the elliptic envelope classifiers, they were the classifiers that presented the performance considerable better than the other two classifiers. We could say that these classifiers they were the best classifiers. If we compare the results between the stealthy and the overt mode, we can see that the general performance of the overt mode is slightly better than the stealthy mode, but this better performance of the overt is just slightly better. The difference is not so significant. Here we have the PCA decomposition of the data for each benchmark, and we can see one more time that the intricated points between the RSA benchmark and also in the DRISC benchmark, they they give us an idea why in these applications the detection is lower than in the other applications. If in the overt mode, if we compare the execution when we use the autoencoder and we don't use the autoencoder, we can see again that there is no significant gain with the addition of the autoencoder. Again, with the one class SVM classifier, we saw that it only increases its performances when we use the autoencoder. This result is not possible to see here because this consideration is based on the result with the malicious function of 10% that is not showed here, but we made this consideration. In other way, we can see in these histograms that again the elliptic envelope mostly decreases its performance when we inserted the autoencoder in the path. This suggests that some classifiers that behave in a different way, they change in a different way his performance when we add the autoencoder. Some conclusions of our case study. With these results, we confirmed the feasibility of detecting stack buffer overflow attacks through anomaly hardware-based detection. We can see that we have a gain of analyzing 8 hardware performance counters in comparison when we analyze just 1, 2, or 4 hardware performance counters. This gives us an insight that if in our hardware architecture, in our performance monitoring units, we have the possibility to track more events at the same time, we will have a better malware detection performance. Also, the hardware-based detection is more effective when detectors are trained for specific applications. That is the case that we show our results. The randomness in the protected application is a challenge in the hardware-based detection, and this was very evident in the case of our RSA application. Other consideration is that the prowess of the local outlier factor and the elliptic envelope classifiers becomes evident. Finally, autoencoders did not bring significant performance, but perform tests with a specifically configuration of autoencoder, and we think that maybe trying to tune the autoencoder, we can maybe have a more gain due to the use of the autoencoder. As a summary of our presentation, we discussed the promising hardware-based malware detection approaches with a case study on a RISC-V architecture. The hardware-based approaches are feasible. We show this. However, implementations must be performed carefully to overcome the obstacles of the poor detection performance. As we can see, sometimes we have some accuracies lower than 90%, and this could be a problem that we need to take care. Hardware-based detection approaches may bring interesting advantages for RISC-V architectures like runtime detection, zero-day malware detection, resilience, and reduced detection costs. The availability of hardware performance counters and the simplicity of machine learning algorithms employed enable the malware and software attack detection close to the local node. RISC-V designs may contribute with architectures properly supporting the hardware-based detection approaches, with reliable and complete performance monitoring units and dedicated hardware for machine learning. We think that this is the biggest contribution that the RISC-V community could bring to this approach, that would be offer a performance monitoring unit that has a great support in terms of hardware events to the upper software level in terms of enabling good machine learning processes and having good performances on these approaches. Future works on the topic may comprise different use cases. With this, we finish our presentation, and more about this you can find in two publications that we recently released. The first is a survey on hardware-based malware detection approaches, and the second publication is a publication about this case study that we performed. And this publication was a preliminary, it shows preliminary results, and it was made in the RISC-V Summit Europe some weeks ago. Thank you for all, and we are available to questions.
So thank you very much, Cristiano and Alessandro, for the excellent presentation. I worked a little bit in the past with kind of this kind of scenario, not that much, but I mean, instructions just not going on, so far away from what we're doing. So thanks for the work. Thank you for sharing these details. So first question for you both: are you involved in any RISC-V test group to help me secure RISC-V from the instruction point of view? Are we involved within the community somehow, or just doing the research?
Not already. We are still doing the research. We have a couple of colleagues that are
so maybe
yeah.
Not, maybe you can join the RISC-V International as a member, and then can help the secure kind of test groups. I mean, with some assessment and education on this front, that would be helpful for the RISC-V as an instruction set. So
it's a very good idea. I'm going to check everything, but it certainly is generally a very good idea. We would really
No,
like to
no
bring
problem. We can check
our.
later. But anyway, so we have some questions in the chat, but most of them were answered by Alessandro.
I tried to at
I'm not
least,
sure
but
if there is any pending questions. I believe
if I
there's one
missed.
pending questions. Yeah, about GitHub resources that was
Yeah,
answered.
as I wrote too many comments.
So
We're
folks, uh, yeah, there are
Yeah,
some
sorry,
questions emerging,
I
so
was
we
just
have some time.
commenting
So feel free,
on.
Alessandro and Cristiano, to reply to those or answer verbally.
Okay, yeah, I'm looking at the comments right now. Just a general comment about the code in general. There are many questions, and I
Alessandro,
replied
not sure it's just
in
me. Not cannot hear Alessandro.
I don't know. Do you hear me?
Me too.
You
I
don't hear
hear
me?
you, Alessandro. I am
Okay,
here.
Rafael, do you hear me now? Okay, well, if everybody hears me, I try to answer, so at least I know that it's going to be recorded. So very quickly on the code. As a group, we have a policy that everything that is going to be published has to be public also in the code, unless there is some NDA that prevents it. So the idea generally is to have a paper, and since this is an ongoing work, so there are still a couple of tasks that we are carrying out that are expanding the results that Cristiano showed you. The idea is to deliver the final code publicly open for everybody at the end of them. So as soon as we finalize everything, it would be open. Regarding the question from Oren, I hope I pronounced properly the name. The work is specific to RISC-V because the events that we considered they were the only available in the PULP platform. Clearly, this makes the work bounded to the RISC-V, but at the same time, it can be expanded to other microprocessors. Other microprocessors are certainly bigger in the number of events, not necessarily bigger in the number of performance counters to track them all, quite the contrary, but this is the main thing. And if I can comment, it's also bounded to RISC-V because it's an open architecture. So as Cristiano was mentioning at the end, our expectation for the future is to bound to the RISC-V even more by supporting maybe a new generation of performance monitoring unit with bigger counters in terms of number, I mean, but also maybe finding out events that are not yet tracked, so that they are not still there to be available, and maybe they can in the future. Okay.
Alessandro, related the question of Oren, I would like to add still, maybe I was not so clear. He asked about how many performance counters we used, and this on our histograms, we can see that for each classifier, we have 4 bars. Therefore, the first left bar is the accuracy related a case where we use one performance counter. The second from the left is the accuracy for the case where we used two two performance counters. The third one from the left is the case where we used 4 HPCs, and the fourth one is the case where we use 8 performance counters. We can see that as much performance counters we use, in general, we have a better accuracy. Just this adding.
So folks,
And
go
yeah,
ahead, sir.
I don't know, Oren, if you asked this new question while I was explaining everything, or it's on top of my full answer. Yeah, sure. Well, you had in the presentation many QR codes. So as soon as the recording will be available, in the first slide about the group, there was a QR code. You can stop there. Use the QR code to go to our website, so to get our contacts even in a faster way. And we are very happy to receive any offline questions slash follow-ups. At the end, since you know the time frame here is not infinitive.
Yeah, that's great. So we are a little bit over time. So I would like to thank you both again, Cristiano and Alessandro, for your time, for all the great explanations and details. I believe that we need to bring you back at some point where when we have more details and more kind of insights to share with the community. But for now, thank you very much for your time. Thank you for your presentation. I'm going to try to publish this on our YouTube by end of tomorrow or maybe next Monday as soon as I can, and I'll let you know. Okay, thank you very much,
Will be
folks.
wonderful. Thank you again for having us here.
Thank you, Rafael, for the opportunity. It was a great pleasure.
Bye, everybody.